Welcome to Unit 7. The next few series of presentations are going to be focusing on Paper 2 of the IGCSE Computer Science syllabus from Cambridge. In this particular lesson, we're going to be looking at the program development lifecycle, but we're going to limit ourselves to the stages of analysis, design, coding, and testing. We're also going to be looking at how a computer system can be composed of subsystems, which are made of further subsystems. So the process of decomposition comes into play here. We're going to be looking at how a problem can be decomposed into its component parts, so you can solve each part on its own. And finally, we're going to be looking at the different methods used to design and construct a solution to a problem. So let's start by looking at the program development lifecycle. When a new program is developed, a lot of professional organizations normally use a systematic and organized way to develop them. And this is called the program development lifecycle. Most of the times when you're coding, you probably just get on a computer and you just start typing. That perhaps works really well for smaller programs. But when you're developing games or working with massive projects for big organizations, that kind of approach doesn't quite work. In those cases, we use a program development lifecycle, which is basically a series of steps that are followed to develop a system or a program. And there are a lot of different types of program development life cycles. For example, cyclic, waterfall, rapid application development, also known as RAD. All of these include the following four stages: analysis, design, coding, and testing. You need to make sure you remember all the bits highlighted in bold for a particular answer related to program development lifecycle. Let's look at the analysis stage. This is the first stage and it involves looking at the problem that you want to solve or the system that you want to create. This problem is explored and is identified at this particular stage, and the requirements of the programs are then listed. Abstraction is used to remove any information which is not required to solve that problem. We also use decomposition, which is used to split the problem into subproblems so you can tackle each of those subproblems much more efficiently. Now, these subproblems allow the developers to identify the requirements for each component part, and then they can tackle those separately in the next stage, which is design. Now, in the design stage, once your requirements have been identified in the analysis stage, the program designers can begin planning how the program will work. And this includes an overview of the program itself, and we use common techniques like creating structure diagrams, designing algorithms using flowcharts and pseudocode, database design, and user interface design. All of these design techniques, which we'll explore a lot more deeply later on, are used in this particular stage to plan your solution. Now, sometimes it can also include a basic test plan. That's also part of the design stage where you plan your tests. However, that's not normally listed in the IGCSE syllabus, but just be aware that that's possible as well. Okay, let's start by looking at a structure diagram. A structure diagram is developed by decomposing a program into subprograms. So you have a problem, which is normally decomposed into four parts: inputs, processes, outputs, and storage. And we normally represent this in a diagram. Now on screen, you see a diagram for a checkers program, which is a game kind of like chess or Go. So the checkers program is split into four parts. The first part is new players, where we add new players. Then there's a new game, so both players can start a game. Then they should be able to make a move, and then we should be able to check who won and who didn't. So each subprogram can be further split down as well. So new players can perhaps be split into player one, player two, and so on. Now, most of the time we use rectangular boxes and lines connecting the various different modules. Once you've decomposed your program into subprograms, you will need to design an algorithm for each of those parts. And this could be the first level, which is below the name of the program itself, or it could be further subprograms which come later on. For example, in the updated diagram that you see on screen, the make move subprogram could include outputting the player's turn, inputting a piece, inputting a move, checking if the move is valid, and then moving the piece itself. So all of those parts need to be completed for make move to be completed. All these individual algorithms would eventually come together to create the whole system. And you could also allocate different programming teams to work on different parts of the program. Now, in an exam, you might be given a text description or module names, and you'd be asked to create a structure diagram, or you might be given a structure diagram and you'd be asked to identify the modules or create the pseudocode or algorithms for various different modules. Another aspect of design is creating flowcharts, and this is a different way of representing an algorithm. Normally we use pseudocode or flowcharts. So each of those little modules, those subprograms, you need to design a flowchart or a pseudocode algorithm. And a flowchart is basically a diagrammatic representation of an algorithm. And you see an example on screen. Again, this is an application-oriented question. So normally they'll give you some pseudocode and they'll ask you to create the flowchart for that, or vice versa. What you should know is the various different symbols that are used. So do pause the video and go through the common symbols that you're expected to know at IGCSE level, including flow lines, which connect different parts together, processes, which is where you do your calculations and your searching and your sorting, subroutines, which could be other modules, and these are normally rectangular boxes with two lines inside of them. You normally have parallelograms, which are basically input and output. So you need to make sure that you use them for both of them, both inputs and outputs. And if you've got an if or a decision to be made, then we use a diamond for that. Now this is normally yes or no or true or false. Terminators, which are used for starts and end of a program, are basically these rectangular ovals, which need to be used as well in your flowchart. So do pause the video and study these symbols. Do look at that algorithm that is on screen and make sure you understand how it works. To create a loop, we just simply link a line, a flow line, all the way back to the previous part, and that indicates a loop. A common question that comes up in the exam is you're given a flowchart and you're asked to trace it and complete a trace table. So they give you some values and you just have to follow the path. Now, the big part of paper 2 is pseudocode, and this is a bit that scares a lot of students when they first encounter it. Pseudocode isn't really tricky. If you know some basic programming, you can get a handle on it pretty easily. It's a lot more forgiving than actual code because you can get away by making small mistakes. Pseudocode refers to any code that is not written on a computer to run, so it's basically fake code. There is no one set pseudocode. Instead, it's a term that is used for any readable code-like statements that programmers should be able to understand. This means it uses keywords and constructs like if statements, while loops, for loops, and these constructs occur in almost all languages, so any programmer would know what to do if they encounter a bit of pseudocode. Now on screen you see an example of pseudocode. Input number 1, and input is capitalized because it's a command word or a keyword, and number 1 is your variable. And similarly, output is capitalized if, then, else, and if are capitalized. Pause the video to have a look at the pseudocode that's in the table. We will be practicing a lot of pseudocode later, so we'll get familiar with all of the different types of keywords. So after design is finished, we've done our structure charts, we've done our flow charts, we've done our pseudocode, we then get down to coding. And in this stage, once you've decomposed your problem into subproblems and you've designed everything, you've got your algorithms, you then start writing the program code in your programming language. And this stage is called coded. Sometimes you have iterative testing because you check your code as you go along, you type it, there's an error, you fix it. And this testing is carried out while the program is being developed. So coding just isn't about programming, it's also about testing as you go along. Of course, there is a formal testing stage after the program is developed. So the testing we were doing during coding is just to make sure the program works basically, and then we formally test it. And this is when you have finished your program, you need to carry out testing to make sure it fully works, does not crash, and meets all the requirements that you planned in the analysis stage. So you will need to identify appropriate test data to use to test your program. And normally there are 4 types of test data: normal, data that the program should accept; abnormal, data that the program should not accept because it has errors; extreme, data that is at the edge of what is allowed. For example, if you've got a range and the range is between 0 and 100, 0 and 100 are basically your extreme edges. And then you have boundary, which is data that is on the edge of being accepted and being rejected. So for example, -1 could be rejected, 0 could be accepted, and 100 could be accepted, and 101 could be rejected. So that would be an example of boundary data. Now on screen you see a testing example, so do pause the video and have a look at the different types of tests for a program that allows the user to enter their age as a whole number between 10 and 100 years. So how would normal test data look like, abnormal, extreme, and boundary? And in the exam, you would need to give examples of test data if a question requires you to. So that's the end of our first lesson on Unit 7. You should be able to answer the following questions. What is a program development lifecycle? So you should be able to give 2 points for that. What are the 4 stages of the program development lifecycle? You should be able to identify those 4 stages. Describe what happens in the analysis stage. 4 marks, 4 key points. Look at what was highlighted in bold. Describe what happens in the design stage. Again, for 4 marks, 4 different things. What is the purpose of a structure chart? Draw common flowchart symbols. You should also be able to create flowcharts and manipulate flowcharts. And finally, you should be able to identify the 4 types of testing, and you should also be able to give examples of that based on a scenario. That's all for this particular lesson. If you do have any questions, please get back to me. Otherwise, I'll see you in the next one.